So hey guys, today we're gonna talk about pure bending. Pure bending is a condition of stress where bending moment is applied to a beam without the simultaneous presence of axial, shear, or torsion force. Pure bending occurs only under a constant bending moment since the shear force which is equal to has to be equal to 0.
As you can see, even if the beam is bent, the member remains symmetrical and it bends to form a circular arc. A cross-sectional plane passes through the center of the arc and remains planar. The top surface of the member decreases and that is why it's called compression, and the bottom surface of the member increases and that is why it's called tension.
The length of the neutral axis does not change even if the member is bent. And y is measured from any point to the neutral axis. And z is measured from the neutral axis to the surface. L prime is equal to rho minus y theta. Deformation is equal to L minus L prime is equal to, we substitute this part to get negative y theta. As we all know, the strain at any point is equal to the deformation over the original length. So we substitute the negative y theta and p theta, so the rho theta. So we get negative y over rho. And to get the maximum strain, we use C over rho. This one is the C and rho. Or rho is equal to C over maximum strain. And this is what we call the ratio of the strain at any point and the maximum strain.
So for our first problem, there's two figure A, figure B. For our figure A, this is the bar of rectangle cross-section in per bending. For our figure B, this is the centroid and dimension of cross-section. So for our rectangle, there's a 0.8 inch given for the width and 2.5 inch for the height. First, let's solve for which is the equation number 1. I is equal to 1 over 12 base times height cube. Then let's substitute the value. 1 over 12 times 0.8 times 2.5. As you can see, 0.8 is the width, 2.5 is the height. So as we compute, 1.042 inch. Then we can solve now for the bending moment. M is equal to 1 over C and the maximum stress. That's for the equation number 2. Let's substitute the value. 1.02 over 1.25 inch. That's the C from the center to the surface. Then 36 ksi, which is the maximum stress. So to compute, bending moment is equal to 30 kPa inch.
we have a bending moment of 25 kilopound inches. And the formula for getting the moment of inertia of a rectangle is 1/12 base times height raised to cube. And to get the moment of inertia of this figure, first we need to cut this figure into 3 rectangles. I1, the base of rectangle 1 is 2 and a height of 1.5. Right, I2, this one, I2 has a base of 2 and a height of 5.5. And I3 is just the same as I1. So we obtain 28.854 inches raised to 4. Then y is the distance from the neutral axis to the point A and B. So to get the stress at point A, we use this formula. Then we substitute the values. Y is the distance from the neutral axis to the point A and B. To get the stress at point A, we use this formula, negative my over I. Then we substitute the values and we get this negative 2.38 kilopound per square inch and negative 0.65 kilopound per square inch.
Don't stress your mind. We come.
In this figure, the cross section has 2 circular holes. And the bending moment is 2.8 kilonewton meter. So first, we have to solve for the moment of inertia. We subtract the moment of inertia of the 2 circular holes from the member. So we substitute the values and we obtain. And to get the stress at point A and point B, we use this formula. And by substituting the values, we obtain negative 39.3 megapascal and 26.2 megapascals.
Assuming that this figure will bend about the y-axis with the allowable stress of 155 megapascal. First, we need to get the formula for the moment of inertia. Then we apply the given values. But this figure is need to be cut in 3 to determine the true moment or the total moment of inertia. So as you can see, we will cut this figure in 1, 2, and 3 parts. So the first part is 1/12 over base. The base is 12 and the height is 200 times 3. This is millimeters. Is equal to 8 times 10 to the 6th power millimeter to the point. Second, 1/12 times 196 times 8 to the cube is equal to 8.3627 times 10 to the 3rd millimeter to the point. And last, the moment of inertia is equal to moment of inertia from the first part. So this is also equal 8 times 10 to the 6 millimeter to the point. So we will add the 3 inertia. The inertia total is equal to inertia 1, inertia 2, and inertia 3. So as we compute, we will get the value of 16.00884 times 10 to the 6. Now, we need to determine the value of C. the C is from the center of the neutral surface to the C is from the center surface and to the neutral surface. So C is equal to 1/2 of the given height. 200 is equal to 0.100 millimeters. So my is equal to 16.0084 times 10 to the 6 times the given allowable stress is 155 times 10 to the 6 over 0.100, and we will get the value of 24.8 kilonewton.
Pretty lies, look me in the face, tell me that you love me, even if it's fake, 'cause I don't
2, 3.
The properties of W4 by 13 rolled section. Here we are given the area, the width, and the moment of inertia. Let's look at this one rolled section. To get the moment of inertia of section B, we need to add a correction to the moment of inertia presented by AD squared. Now, for both sections, we multiply the inertia of section B by 2 and we obtain 39.286 inches to the 4. To get the allowable stress, we use the formula for factor of safety. Then we get 19.33 KSI. And for the bending moment, since we have the allowable stress and the inertia, and all we need now is the C, which is the width, 4.06. Solving it, we get 187.1 inches. In this figure, we will find for the bending moment. First, we need to find the moment of inertia of the circle. And we use the formula pi over 4, r raised to 4 minus r raised to 4. Then we substitute the values. Take note that you should be careful on substituting the values. Here, we are using the outer and the inner diameter. And then we obtain 52.7 times 10 raised to negative 3 and inches raised to 4. And C is the distance from the center of the surface and to the surface, and computing for the bending moment, we substitute the values and obtain 1.405 kilopound inches.
Behind closed doors, I'm a fool for your love.
With the given value, allowable stress of 12 KSI in tension and 16 KSI in compression, determine the largest bending moment again. Another hard problem. What we will do, guys? So let's determine first the areas of the figure to solve for the Y bar. So 2.25 for the first area, 2.25 for the second. Y bar outer is equal 1.25, 0.25. Area of the total is 2.8125, 0.56. If we complete the total of this, 4.50, and complete for the total of this, 3.375. So y top is equal to 2.0 minus 0.75 is equal to 1.25 inch. So again, we will solve for the moment of inertia. 1 over 12 b sub 1 b sub 1 h to the cube plus a sub 1 b sub 1 is equal to 1 over 12 times 1.5 times 1.3 raised to 3 plus 2.25 0 times 0.5 raised to 2. So, like always, we will solve for the total of inertia. So, the value we will gain is, where is it? So, here, 1.59. So, the stress is equal to stress, moment of inertia, and y bar. That's why we get the y bar here. So 0.609375 inch to the fourth. So the moment bending, to know the largest, we will know the moment from compression and tension. So moment bending in compression is equal to 16 times 1.5975 is equal to 20.4 kb/inch. So moment in tension is equal to 12 times 1.59, 37 over 0.75 is equal to 25 kb/inch. So the largest is 25 kb/inch. Okay.
As we can see here, from the previous problem, we changed the value of the outer diameter, or this one, 0.2 inches, and to solve for the moment of inertia, we should use this formula and we should substitute the values, and again we should be careful in using the diameter and substituting the diameter, because here we should use 0.5 inches plus 0.2 inches, so we use 0.7 inches and we get 139.49 times 10 raised to negative 3 inches raised to 4, and again we use the C as 0.7 inches. And computing for the bending moment, we substitute the values and we obtain 3.19 kilopound-inches.
So guys, we have a similar problem like the earlier in the earlier. So we got 50 millimeter, 40 millimeter on top, 30 millimeter on the height, so 20 on the base. So first we need to determine the y bar. So to determine the y bar, we need to get the area of each part. Area 1, area 2. So the value in area 1 is equal to 600 and the value of in area 2 is 300. So we're getting need to get the y bar, the height of the y bar. So half of this is 20. In the part area 1 is 22.5 and in the area 2 is 7.5. So multiply the area and the height. So we get the 13.5 times 10 to the raised cube. So into 300 times 7.5 is equal to 2.25 times 10 raised to cube. So find the total, 100, find the total, 15.75. So to compute the y bar, we need to divide 15.5 over 900 is equal to 17.5. So we need to determine the height. which is the center on the top and on the bottom. So 30 minus 17.5 is equal to 12.5. So in the bottom, 17.5 is equal to negative 0.0175. So in the first lesson, we're finding the moment in inertia again. So 1/2 base is 40, height is 15 cube. So plus the area 600 times 5 squared is equal to 26.25 times 10 cube millimeter to the fourth. So inertia 2 is equal to 1/12 times 20 times 15 cube plus 300 times 10 cube is equal to 35.625 times 10 to the cube millimeter to the fourth. So get the formula of stress is equal to bending moment y over I, and bending moment is derived by bending moment is equal to stress, inertia, and y bar. So moment is equal to 24 times 10 raised to 6 times 61.875 times 10 raised to negative 9. So that's compression. So for tension is M is equal to 30 times 10 raised to 6 times 61.875 times 10 raised to negative 9 over 0.0175. So we get the total toss here 118.8 Newton per meter, 106.1 Newton per meter. We're finding for the lowest, which is 106.1 Newton per meter. That's all.
Yeah. Ooh, I fall apart. Down to my core. Ooh.
Next problem. We need to find the stresses at the top and at the bottom of the figure. First, we divide the figure into 3 parts. And then make a table where we put their area and y sub o. And then we multiply the area and y sub o. We get the total of the area and multiply with y sub o for us to get y bar, which is our new to get our y bar. And then we find the moment of inertia of the figure by adding all moment of inertia for the 3 parts. For the first part, this figure has a base of 8 and a height of 1. We get 59.94 inch to the fourth. The second part, the figure with the base of 1 and height of 6, we get inertia of 21.63 inch to the fourth. The third figure with the base 4 and a height of 1, we get 73.54 inch to the fourth. We total those and we get 155.16 inch to the fourth. For us to solve for the stresses at the top, we need to determine which one is the figure and the bottom of the figure by looking at the turn of the moment. And to solve this, we use negative my top over inertia. So substituting the values, we get negative 10.38 KSI. Since it's negative, it's compression. And for the bottom stress, we substitute the values, we get 15.40 KSI tension.
Thank you for watching. I hope you like the lesson. Hope Please comment and like and subscribe. Thank you for watching.